begin with a word of prayer. So, Heavenly Father, we thank you for this day. Thank you for these students. I just pray that you be with us today. Help us to, again, Lord, glorify you in what we do, Lord. In your name I pray. Amen. It now occurs to me that I have not fixed the focus on this silly camera. It's going to, if I don't do this, it goes all blurry. And it's great sadness. Come on. It's very annoying. It gets to these automatic presets, so it won't. I have to get it to like the 25-foot setting, but that only comes up. I don't know how it comes. It changes its mind every time. Okay, guys. So what's our first move there? Man, stupid thing. I will eventually stop playing with this thing. If it's any consolation, I'm not enjoying it. Come on. It'd only go to 15 feet. All right, well, it's maybe blurry. Hopefully it won't be too blurry. There we go. Roughly speaking. All right, so first order of business. And we're also going to calculate the arc length from 0 to 2 pi. It's an interesting calculation. So dx dt, I'm going to start out with finding the horizontal and vertical tangents, right? So the dx dt is minus sine t. Dy dt is 1 plus cosine t. As we discussed last time, this equal to 0 and that equal to 0 have nice solutions. This implies that t is an element, well, it's equal to what? Equal to n pi for n in the integers, right? And this implies that t is equal to 2k plus 1 times pi for some k in the integers, right? And the thing that's right in front of me, it's like, duh, is that they have common zeros, right? Like any odd integer multiple of pi has both dx dt equal to 0 and dy dt equal to 0, right? Right? Like, duh, obvious. It's right here in front of us. So if n is odd, then dx dt and dy dt are 0 at t equals to n pi, right? If both dx dt and dy dt is equal to 0, that's a place where the graph may have a cusp in it, or it may just be a place in the graph where the curves, where the path stops and then starts again smoothly. And you can't know in general without just doing further analysis. It happens for this graph that they're actually cusps. But how about the n is even, though? If n equals to 2k, right, for some k in the integers, then what? We have, well, if n is equal to, okay, so if n is equal to 2k, what happens? dx dt is equal to 0, right? But dy dt is equal to what? One plus the cosine of what? T equals to, t equals what? T equals to, yeah, sorry, I'm an idiot. 2k pi, right? Right. So, and I'm referring to that n up there, right? So, in other words, t is equal to 2 pi k. What is the cosine of 2 pi k? Easier than that. I mean, you're half right. Just 1, right? This is always 1, categorically so. 0, 2 pi, 4 pi, minus 2 pi, minus 4 pi, minus 16 pi. Cosine of those things, 1. So this, come on. What on earth? Why? Goodness gracious. I give up. I'm sorry. Maybe I should just call it a day. Good gracious. 1. 2. Yes. So, yeah. So those are what? If you have dx dt equals to 0 and dy dt, those are vertical tangents, right? So we have vertical tangents where? Vertical tangent lines at t equals to 2 pi k, which corresponds to what in terms of x and y? X equals to cosine of 2 pi k, aka 1, and y equals to what? 2 pi k, sine of 2 pi k is 0, right? So in other words, the Cartesian equation of the vertical tangents is just x equals to 1. If you want to parametrize it, it's x equals to 1 with y equals to 2t. If you use the colliding tangent line for the colliding tangent line for the vertical tangent would be what? We would have x equals to 1, and we would have y is equal to 2 pi k plus t minus 2 pi k parentheses. And what's the y? 2. This right here is just the scalar version of r of t is equal to r of 2 pi k plus t minus 2 pi k times r prime of 2 pi k. Okay, there you go. That's just... Sorry, I know it's a little bit... I'm doing it for all of them at once. So maybe it'd be better if I just did it for one. But, I mean, in particular, there's a vertical tangent line. Let's think about just k equals 0, 1, and minus 1. What are those ones? Let's see here. So I'll try to draw it on that scale, see if we can get it. Oh, there's a head in the way. That's too close. All right, I give up. I'll leave it to you. I'll leave it to you. Yeah, I'll leave it to you. I've tried this before. It never turns out well when I try to do my own camera work. Let's see here. That should behave. All right, so where are the vertical tangent lines? Let me just draw them in blue. There is one where x equals to 1, y equals to what? 0, right? There's a vertical tangent line like here. Where's the next one? And I'm just going to draw it kind of like locally because that's still not quite tight enough. I mean, that should be closer, but I'm just going to not quite do it to scale. The next one is at 2 pi, right? There's another vertical tangent line like here, right? There's another vertical tangent line down here, right? Possible cusp in the graph where? Odd pi, right? So if we put in t, if we put t equals to pi, where's t equals to pi? Notice if you have you have an odd integer multiple of pi, like pi, 3 pi, 5 pi, minus 5 pi, all of those have cosine as minus 1. All the cusps are at minus 1. So like the first one, minus 1, so there maybe is a cusp, let's see here, same distance, like over here. There's one here, like that. There's one up here. So these are going to be possible cusp. Now let's see here. We can get a little bit more data. How about the y-axis? Where does this thing cross the y-axis? Just an additional. How about y-axis crossing? How do we find those? We're looking for x equals to 0, right? If we find those points, then that should give us a pretty good picture of what else is going on. So let's see here. X equals to 0. So that's cosine of what? T equals to 0. In other words, what? T is equal to plus or minus pi over 2, plus or minus 3 pi over 2, and so forth, right? So we have y, it crosses the y-axis where? Like, well, I shouldn't say that. Excuse me. That is the time that it's at x equal to 0, right? Where does it cross the y-axis here? What's y equal to? Y is equal to t plus the sine of t, right? So let's see here. That goes to what? For example, pi over 2 plus 1, or minus pi over 2 minus 1, or what? Minus 3 pi over 2, right? Minus 1. Yeah. Well, wait a minute. Plus 1, right? Because the sine of minus 3 pi over 2, excuse me, the sine of minus 3 pi over 2 is minus the sine of 3 pi over 2. Sine of 3 pi over 2 is just minus 1, right? So it's minus and minus 1. I think that gives me plus 1 there. I could be wrong.
If the negative 3 pi over 2 is at the same position as regular pi over 2, so it would be plus 1, wouldn't it? Is there terminal?
Yeah, I mean, that was what I was reasoning to, but yeah. I mean, basically, I'm saying sine of minus 3 pi over 2 is 1. I think we agree. Yes, they're 2 pi separated in the graph of sine, absolutely. Okay, so my point then is the most interesting one for me is this one. This one's about what? This is about 2.57-ish, right? So that's, so let me try to put these points in red, and then I'll or maybe not red, maybe, oh, fine, red. No, green. I can't make up my mind. So 2.57, well, that's kind of like here somewhere, right? And let's see here. This one is what? This is about minus 2.57, right? So that's like here, right? What's 1 minus 3 pi over 2? I don't have a good sense of that right off the top of my head. Could you guys punch the numbers for me so I don't deceive myself? So I will do that. I mean, I want to say like minus 3.5, 3.6 minus 3.6. It's, golly, I think it's symmetric more or less over here. So the next, I probably need to go one more to be clear. If I go up here, I get 3 pi over 2 minus 1. So what was that?
Negative
3.71. Okay, and how about 3 pi over 2 minus 1 is approximately what? Oh. Sadness. So that's 3.14, of course. So it's like, so they're like straddling. Anytime you have a cusp, you're crossing the x-axis. Well, I'm arguing that from this graph, it starts to be clear that they have to be cusps, right? It can't be like a vertical tangent or something in disguise. I mean, they have to be cusps, given the rest of the data we have here. These points have to be cusps. And the graph then has to look something like this. Roughly speaking. So you have vertical tangents here, and you have these cusps in the graph where the velocity vector drops to 0 because the tangent line is going, like, as it's approaching this way, right? The tangent line is going like that, right? But after you go past that point, the tangent line is going like this, right? So the only way the velocity vector can change directions like that is if it goes to 0. Yeah. Questions? Something interesting, you can actually calculate the arc length of this without too much trouble. Check it out. So the arc length, let's suppose we just want to find the arc length from 0 to 2 pi for t. So let's see here. S should be equal to the integral from 0 to 2 pi of the square root of what? dx dt squared, right? Plus dy dt squared dt. What is that? Let's see here. dx dt, well, we figured that out. That's, so we got what? We got sine squared t, right? Plus, and then we've got ourselves a 1 plus cosine t quantity squared, right? Let's do the algebra. What do we got? So FOIL that thing out. We get sine squared plus 1 plus 2 cosine t plus cosine squared. Well, something really nice happens, right? The sine squared plus cosine squared and the 1, these all combine together to give you what? Yeah, we get integral from 0 to 2 pi of the square root of 2 times 1 plus cosine t. I'll just factor out the 2. All right, but think about this. 1 plus cosine of t, right? You can rewrite. See, 1 plus cosine of t divided by 1/2, right? That's equal to cosine squared of t over 2. Now, we usually start with like a cosine squared of theta over here, right? And then we get a 2 theta over there, but if you do the other way, then you have to divide by 2, right? So check it out. This is really then the integral from 0 to 2 pi of the square root of 4 cosine of t over 2 quantity 4 cosine squared t over 2 dt. Square root of square, yay! So we get integral from 0 to 2 pi 2 cosine of t over 2 dt. And let's see here. Now, intuition, what should you have, like, answer? Let's just think about this for a second. I told you guys last time, so we're really just looking at this part of it, right? Right, this is the part we're calculating the arc length of, okay? And remember what I said? It's basically you're just taking the circle, right? And just drawing it, translating upward. So what should the arc length of this be? My naive thought was 2 pi, because it's a unit circle, right? Just written by going like this. But my intuition's wrong. It should actually be a little bit more than that. Let's see how that happens. So this would be 4 sine of t over 2, evaluated from 0 to 2 pi, right? Which is what? 4 times the sine of pi minus the sine of 0. Oh man, it's 0. The arc length is 0. Oh man, my picture must be really wrong. It doesn't look like 0 arc length. How have I bamboozled you guys? I think that's my first time saying bamboozled this semester. I mean, you know it's wrong. 0 is not the right answer. Where's my mistake? Yeah, it's just 1 point, so we can integrate from there and then start again. That won't change the integral. 1 point. Nice try, though. Thought crossed my mind as well. Whenever you get something you don't understand like this, there are a couple things you should look for. The one is that you've divided by 0. The other is that you've somehow inadvertently taken the natural log of a negative number some way. But the more likely thing is the following. You've taken the square root of something squared and assumed it's positive. But when we take the square root of something squared, we get the absolute value of the thing. So you see this is right here. No. And that matters, you see, because cosine does this as you go. I mean, this cosine function does that as you go from 0 to 2 pi. Well, let's see here. 0 to 2 pi makes this go from 0 to pi, actually. So it's like you're basically getting that much, right? So when you integrate this thing without the absolute values, you're getting this piece, and they're canceling, and that's why you get 0. That's nonsense, right? I mean, the square root of something squared should be positive. You should put the absolute value here is the point. Because it's square root of a squared, right, is the absolute value of a. That's the thing we're glossing over, and we can't. If we do, we get the wrong answer. Now, once you do this, it's easy by symmetry to do this calculation. Instead of doing what I did, what should I do? How about this? We just double up. So given the shape here, I should just integrate from 0 to pi, right? And 4 times the cosine of t over 2. So I just doubled half of the integral, right? That they're basically saying integral from 0 to pi is like this much. And so I just doubled that up by symmetry. And that gives me 8 times the sine of t over 2 evaluated from 0 to pi, which is 8. Which is kind of a pretty result. The arc length of the cycloid, unit cycloid, going from 0 to 2 pi is just 8. In comparison, the arc length of the unit circle, 2 pi, about 6.28, right? So you've added by, and that makes sense, right? As you're translating it, you're going over a slightly longer distance according to, your vertical translation. But it's not just, it's not just 2 pi plus 2 pi either. You might naively think that, right? Because the length of, you've translated it, that you've gone from your starting point to your ending point 2 pi vertically, right? So if you're, another naive idea might be it's just the unit, it's the arc length of the unit circle plus 2 pi, but that's also wrong. Because the distance traveled it's more complicated. So anyway, I'm gonna shut up about that. So you guys have, that's now I fixed it, and we can go on with our life if you want. You guys have questions? Anything, really? Floor is yours. I do need to come back and talk about the second derivative stuff at some point, but I'm going to put that off and let you guys ask questions for a while. Yep. Yeah, but the thing is, in that way of doing things, if I said, okay, I'm going to integrate from 0 to pi, and then I'm going to integrate from pi to 2 pi, the pi to 2 pi integral would have been negative. If you still made the same algebra mistake there, like just the square root of the square is just the thing again. The point is the square root of something has to be non-negative by definition of square root. So if I'm taking the square root of a squared and a is negative, I have to put minus a if a is negative. I have to put a if it's positive. In other words, I have to put absolute value of a in all cases. Yeah. It's algebra. We can never escape it. What can I tell you guys? I was very happy. There was a student in the second section. I didn't work it out in class. I just had it written down on the bottom of the board because I just plugged this thing in Wolfram Alpha and I got 8. And I was like, well, that's cool. I didn't know that this was an easy arc length. This is a pretty easy arc length example, right? It's not a bad one. So he was like, I got 0. I don't understand. And so we looked at it after class and figured this out. So you guys have questions? Let me ask you a different question. What would you like to see me do more examples of? What do you think you need to work on the most in this chapter at this point? A hypocycloid. Ooh. I know I'm going to. Sorry, I should not look at that one. A surface area problem. Could be arranged. All right, here we go. Ooh. Well, this looks like... Let's look at number... well, yeah. Have I assigned number 8? Yeah. I'll probably regret this. It does look a little bit scary. We've got x equals cosine cubed. Y equals sine cubed t. And we have 0 less than or equal to t less than or equal to 2 pi. We're given a number of tasks. We're supposed to find the length of the curve, locate the centroid. Let me tabulate my jobs. Let's see here. Length, I'm supposed to find the length of curve. Find the centroid. What else am I supposed to do? And then surface area. Of surface obtained by revolving curve. So much writing. Curve about x-axis. Oh, thank you. Yeah, I said pi over 2, right? But I wrote 2 pi. All right. First things first, length of the curve. So we got what? We got dx dt is equal to what? Minus 3 cosine squared t sine t. dy dt is what? 3 sine squared t cosine t. Now, if I'm smart in this problem, you know what? Every single part of this problem involves ds, right? Let me just enumerate the ways. This length of the curve, we do what? We do integral of ds, right? The centroid, we're calculating x bar, which is the integral of x ds. And, oh, I'm sorry, I need to call this thing L. So like 1 over L that, right? And y bar is 1 over the length of the curve times the integral of y ds, right? That's that. That's this. Surface area, what do? Well, surface area, as we worked out the other day, well, that's the integral of 2 pi y. 2 pi, is it 2 pi y ds? How'd it go? Let me think about that for a second here. So we're looking at it like this. Yeah, that was my ds. This was y. So the dA was 2 pi y ds, and then you add it up. Yeah, 2 pi y ds is the integral. That's the surface area. And but the point is ds, I think of ds as its kind of like own little thing, and there's basically 2 ways to calculate ds, right? You either do ds, well, there's 3 ways, right? In the world of Cartesian variables, ds is the square root of, well, you can do what? You can do dx dt squared plus dy dt squared dt, which is what we'll do. You can do square root of 1 plus dy dx squared dx, that's the graph, right? And we also found in polar variables, what do we find? We found, how did it go? Man, I forget all of a sudden. Well, we had ds squared was equal to dr squared plus r squared d theta squared, basically, is how I remember it. And if I divide this by d theta squared, I get like, or I factor out the d theta squared, I get ds is the square root of like 1, excuse me, r squared plus dr d theta quantity squared d theta. So these are my 3 go-to ways of calculating ds, parametrically, for a graph, or for polar coordinates. That's it. And then, so then I just have to plug these in to these central geometrically motivated formulas in the different cases, and that's how I calculate everything, really. Okay, so this problem. My point to you is the first thing you should do in these homework problems is to find ds, and then you use it for all things that you're asked, right? So what's dx dt squared here? What's dy dt squared? Looks like I've got a 9 cosine to the 4th. Sine squared t. Well, that's hopeful. And I've got a 9 sine to the 4th. Yee. Kind of scary. Cosine squared t. And then I'm adding these. So, yeah, add these. What do we get? Nine times what? Cosine to the 4th t, sine squared t, right? Plus sine to the 4th t, cosine squared t. Can you guys think of any ways we can simplify that? Ooh, what's common here? Yeah, there's a sine squared t and a cosine squared t. This is actually not too bad. And then what's left? It's bark is worse than its bite. Let's see here. So this is 9 sine squared t cosine squared t. And so what do we find? ds is equal to 3 sine t cosine t dt. That's half the battle. Now we just have to integrate that thing various different ways, right? That's your ds. Now, you're like, wait, hold on a second there, mister. You just got done making fun of us for not remembering that the square root of something squared was the absolute value. Okay, I was making fun of all of us. All right, honestly, I did that one on purpose. I do make mistakes that are from the heart, but this one was actually from my mind. So, like, is this an issue here? I just took the square root of something squared. Am I in danger? See, because ds, I'm using this guy up here, right? Square root of that gave me this. What's my domain? That's the key. We're between 0 and pi over 2, right? That's quadrant 1. That's where both sine and cosine are positive. This is the world of happy acute angle right triangle trigonometry. All right, so there you go. What's the length of the curve then? L, integral of 3 sine t cosine t dt, 0 to pi over 2. May I recommend to you a u substitution? This right here will be your du. This is your u. Change bounds, what do we get? 3 integral. If u is equal to sine t, u of 0 is 0. If u is equal to sine t, sine of pi over 2 is 1, right? So when I change the bounds, I get integral from 0 to 1 of 3 u du, which of course is 9 half u squared, evaluated from 0 to 1, gives me 9 halves. There you go. That's the length of the curve. The length of the curve is 9 halves. The length of the curve is 3 halves. Yes, thank you. What is wrong with me? So many things, so many things. All right, 3. Which 3 would you like me to erase? The one outside? All right. By popular demand, I'll erase the 3 outside the integral. There we go. For some reason, I also agree with that. I don't know. It was the... Yeah, whatever. Anyway, so 3 halves is the length of the curve. Now the centroid, then. What do we do? Let's keep it moving here. Centroid, x bar, 1 over L, integral of x ds. What that means in terms of the parametrization, well, that's what? 2/3, right? Integral from 0 to pi over 2. What's my x? What do you put for x? Well, you put the parametrization, right? The parametric formula for x was cosine cubed. So I've got cosine cubed t. My ds, remember, was 3 sine t. Looks like a job for u substitution. And I think I'm going to make a u equals cosine substitution this time. So if u is equal to cosine t, then du is minus sine t dt, right? So I'm going to put a minus out here to account for that. And I've got u to the 4th. There's a 3 inside. I could have canceled those if I was a civilized human being, but it's too late. Du. Let's see here. U of 0 is what? U of pi over 2 is what? U of 0 is 1 this time. U of pi over 2, 0. So we get 1 to 0. Now, I don't like that, so what I'm going to do is cancel the 3's and flip the order of the bounds as to get rid of the minus, and that gives me u to the 4th du. The answer, 2/5. This problem's actually kind of pretty. I'm starting to like this problem. Y bar is what? The integral of u to the fourth is u to the fifth over 5. Put in 1, you get 1/5. Put in 0, you get 0. So 2 times 1/5 is 2/5, yeah. All right, so the next one I've got 2/3. Again, that's 1 over L. Integral from 0 to pi over 2. Sorry, I mean to write. There's one other step I'm trying to write so you understand what I'm doing. Generally speaking, the centroid is 1 over the length of the curve times the integral of y ds. We're calculating the y-coordinate of the centroid. In the discussion we had with you guys the other day, I put a lambda in here, right? I put the lambda equal to 1 because we're assuming a uniform mass density of the curve, which gives us the centroid, the geometric center. Okay, so that actually is what? This is 2/3. Integral from 0 to pi over 2. Y is what? Well, y is sine cubed. And ds is what it is. It's 3 sine t cosine. You see what I'm... you notice here, guys, if you don't think about this conceptually as I am, think about the ubiquity, the universal application of ds in these different formulas. If you were not thinking about this correctly, if you were just plugging and chugging without conceptual clarity, you might have just calculated this 3 times by now, and that would be dumb, right? Like if you're just looking at this as a formula that you plug these things into, if you're not really paying attention, if you're not careful, you might find yourself calculating that like 3 different times. Now, you guys are lazier than that, I hope, right? So the first time you do this is the last time you do this, right? I hope. But there's Facebook and distraction and things like that, right? And so, do you guys actually check Facebook? I think Facebook is mostly for like moms, right? I don't know. Is that fair? Do you guys even care about Facebook?
I would say
It's dying. Because I think middle-aged people are too involved in Facebook for it to be cool with you guys, right? Seems like you want some sort of platform which is disconnected from your parents. Be my guess.
Never done Facebook.
What's that?
Never done Facebook.
Yes, I have never done the Facebook as well. I stand by my decision. Let's see here. Signed to what about Snapchat? I'm on the MySpace. See here, no. So this will be u this time. This is du. And we integrate. This gives us 2 integral from 0 to 1 of u to the 4th du, which again gives us 2/5. Woohoo! So put these two together. What do we learn? Centroid at 2/5, comma 2/5. There's the location of the centroid.
So sine of t is du, not sine of the fourth.
I'm saying, sorry, I mean this is u to the 4th. Yeah, fair. Yeah. U is equal to sine t. Yeah. If I made sine to the 4th u, then I'd be in trouble because du would then be 4 sine cubed times cosine t dt, but I don't have a 4 sine cubed to use after I make u equal to sine to the, see, that wouldn't be good. Yeah, we want to make u equal to sine. That works. Okay, if I put this problem on the final, then I don't even have to test u substitution. It's already got u substitution in it, right? Sounds good to you? As long as you're telling me, as long as you're telling me this exact problem is going to be on the final. Yeah. You guys are. The semesters go by, your faces look different, but you guys all say the same thing. Okay, then the surface area. What? again, integral over the curve of 2 pi y ds. And that's the integral from 0 to pi over 2 of 2 pi sine cubed, right? And then we've got ourselves a 3 cosine t sine t dt. That's our ds, right? Which gives us 6 pi integral of 0 to pi over 2. How many sines do I have? Sine to the 4th. Man, this is did we just do this integral anyway? Yes, we did. So we already know what that works out to. That works out to 1/5. So there you go, 6 pi over 5 surface area. Not that I don't trust you guys, but I don't trust you guys. Let me check our answer. Wait a minute, can I check my answer? Did I bring my... let me try to check my answer. Which problem? We're number 8, right? Man, did I not save it? That was a Jordan call. Mildly disturbing. Let's see here. Here. Using bird calls to find your friends in cafeterias. Yes, this is interesting. I'm almost. Oh, come on, stupid website. Sorry, I'm there. I'm almost there. I missed the wrong Wrong button. Here we go. Come on. What, we were on 10 point what? So the answers, I will read them, you check them. The length was 3/2. The, he's calculated, okay, the 2/5, 2/5, and 6 pi over 5. Yeah. Yay, we can do math. All right, so what else would you guys like to know? We probably should go. It would probably be wise to go back and just do some problems from just starting earlier in the section, earlier in the chapter, and just try to do some problems, just rapid fire, just go through, just do problems. So I'm going to go back here, section 10.2, start there. So let's see here. How about this one? This is problems from section 10.2 on polar coordinates. All right. Number 37. X equals to 2. Change to polar coordinates. Number 40. X squared plus y squared equals to 9. Change to polar coordinates. Let's see here. X squared minus y squared equals to 4. This is number 44. Change to polar coordinates. Let's see here. Identify the curve and write in rectangular. Number 40, number 50, let's say, well, that's too easy. 51. Theta equals to pi over 3. 57. Tangent theta equals to 2. That's still the same stupid question. Number 58. R is equal to 4. Sine of theta plus pi. All right, and each one of these we're supposed to basically take it and put it into the other world. All right, so like we're given either the Cartesian or the polar, and we're supposed to find it in the opposite language. So the first couple are pretty, like, you guys tell me, what is this? In polar coordinates, what is this? R cosine theta equals to 2, so therefore R 2 over cosine theta would be sort of the standard presentation of that, right? This one is just what? R squared is equal to 9. So you could write that as R is equal to what? Plus or minus 3, I suppose, but my heart just wants to tell you it's R equals to 3, and that's all that matters. I mean, R equals minus 3 is redundant. It's the same circle, right? So nothing is lost by just saying R equals 3 there. X squared minus y squared equals to 4. Well, that's R cosine theta squared, right? Minus R sine theta squared, which is otherwise known as R squared times cosine squared theta minus sine squared theta equals to 4. So I suppose I have R is equal to plus or minus 4, bless you, plus or minus 4 divided by cosine squared theta minus sine squared theta. And I could use half-angle identities and stuff to simplify that. I'll just leave it like that for the purposes of our discussion here, right? That's what I meant to write. Sorry about that. So this should be 2, right? Yeah. Thank you. Okay, so that, I mean, all right. these problems, they're really not complicated, right? You just plug in x equals to r cosine theta, y equals r sine theta, and just solve for r, basically, right? These last ones are maybe a little bit more subtle. So this theta equals to pi over 3 is what? In terms of Cartesian, what's its Cartesian description? This may be useful. Tangent theta is equal to y over x, right? So that tells me tangent pi over 3 is y over x, or y is equal to the tangent of pi over 3 times x. Now, tangent of pi over 3 is the sine of pi over 3 divided by the cosine of pi over 3, which, by the way, is root 3 over 2 divided by 1/2. So, in fact, this is the square root of 3 times x. Y is equal to the square root of 3 times x. That's not quite right. Why? It's easiest for me to communicate to you with a picture. Theta equals to pi over 3 is really what? It's a ray like this, right? So all I was doing there was finding the equation of that line. But to be clear, it's not really the line, it's just half of the line. There are various ways you could capture that. I think the easiest thing I could think to say would be x greater than or equal to 0, right? And you can debate whether or not we should throw in 0. Make sense? How about this one? Tangent theta. Well, that's kind of the same example, right? This gives us what? It's the same example, but it's not. This actually does give us 2 is equal to y over x, right? So therefore, y is equal to 2x. The thing about tangent theta equals to 2 is there's more than one. What are the solutions to tangent theta equals to 2? If you think about tangent theta, right? It's like this, right? But it's also like that, right? However you want to plot it. If you draw the line, the horizontal line y equals 2, right? There are two solutions. There's this guy, but there's also that guy, right? This is actually what the calculator would give you. Theta is equal to inverse tangent of 2, right? This over here would be theta is equal to inverse tangent of 2 plus pi. Geometrically, what's going on is you've got, on the one hand, this, which is at theta equals to inverse tangent of 2. It's nothing terribly pretty. It's a line with slope 1, right? The other half of that line is given to you, right, by this one. Pi over, pi radians, it's the opposite side. And so that's where the other half of the line comes from. So it's actually quite different. Theta equals pi over 3 is a ray. Tangent theta equals to 2 is a line, because tangent theta of 2 includes two rays. The ray at inverse tangent of 2 and also the inverse tangent of 2 plus pi, right? So there's that. Any questions? I'll take a breath. How about this one? Yeah, adding angles will make this simplify. Sine theta cosine pi plus 4 sine pi cosine theta. Of course, that's 0. So we really just have what? Minus 4 sine theta, right? Also known as minus 4y.